recall that last time we talked about behaviorist theories. In attempting to create a theory of learning that avoided representations, expectations, and other unmeasurable concepts, researchers in the field of learning actually became increasingly incapable of explaining even something pretty straightforward, like learning without rewards, or the fact that rewards are relative. In addition to the issues that we raised in the last lecture, the restriction on talking about mental states and processes meant that learning theories were unable to explain some very important phenomena in the area of language processing. Consider the following 3 sentences. We have to be at school by 6 p.m. The performance begins at 6 p.m. At 6 p.m., the play will start. They all mean more or less the same thing, right? But these are 3 quite different stimuli from a behaviorist or conditioning approach. And so it then is difficult to explain how these 3 different sentences are understood in the same way by the person hearing them. If we only have behaviorist and conditioning approaches to work with, then we have to resort to the very cumbersome idea that over time, all 3 sentences have become associated with the same response, showing up at school by 6 p.m. And that's problematic because, as we noted last time, once you have one stimulus associated with a response, it's not so easy to learn a new association to that response. Remember the example? When bell ringing was associated with the arrival of meat powder and therefore salivation, and then you add a light to the bell, the light just didn't work as well, and in fact, sometimes animals didn't learn to salivate to the light at all. Once we allow ourselves to talk about meaning and representations, however, it's very easy. While the surface form of the 3 sentences is different, the underlying meaning for the person, the information they contain, is the same. In other words, there are 3 different ways of conveying the same information, and they're going to result in the same behavior. Many other aspects of language use were difficult to explain with behaviorism, like the way people can generate many different sentences that are all grammatically correct. Early learning theories require that we were exposed to those sentences before we could generate them, but this isn't the case. People make sentences that they've never heard before. People make sentences that no one has ever heard before. And a person's ability to create a new sentence that they've never heard before only works if we have the idea of rules. This is the idea that there are rules about how words can be combined, and a person knows the rules and can then use them to make lots of different sentences. But rules aren't observable parts of the environment, and they're not an observable behavior. The idea of rules, again, means we have to imagine stuff inside people's heads, and that's completely unacceptable in a classic behaviorist approach to learning. And that classic approach only recognizes stimuli we can see and behaviors we can measure. As conditioning paradigms were running into trouble, there were actually some exciting developments going on in computing, including the development of the first computers. And this gave rise to a corresponding development that's referred to as information theory. The language and the concepts in the computing world turned out to be helpful in thinking about the way the human brain might learn. Information theory emphasizes how information is coded and recoded, and how it can be decoded or understood as it gets transferred across various media. So a piece of information I'd like to give my husband about when we need to arrive at a school performance moves from a thought or a piece of knowledge I possess to a series of sounds, words, which he can then recode into information and use to respond appropriately. From this perspective, we can think about learning as the acquisition of new information and the ability to use that information in some way, to repeat it, as is the case often in more academic kinds of learning, or to make use of that information. For example, when we learn how to apply for a driver's license by reading a website, and then we make use of that learning by actually going through the process of applying for the driver's license. So in this way, learning occurs as people take in, store, and then use information. Today, we'll focus on 3 issues. First, what is this information processing approach anyway? And second, how do we know this approach is useful or needed? And third and finally, does this approach actually better let us make sense of the way that who, what, when, where, why, and how we learn matter? What does an information processing approach to learning mean? Well, for learning, an information processing approach means that learning happens as people encounter information, connect it to what they already know, and as a result, experience changes in their knowledge or their ability to do certain tasks. The kind of information we encounter can actually be quite varied. So we can think of classroom learning as offering certain kinds of information, but also if you learn a new dance, you can think of the process of watching the new steps and sequence, recoding that visual information into a mental representation, and then translating that representation into a motor movement sequence as you repeat the steps you watched. So both learning and the demonstration of learning can be thought of as translations of information from one medium into another. An information processing approach identifies different stages of the learning process. Initially, new information must be encoded, that is, translated from perceptual experiences into a kind of representation in the mind. Now, once it's there in our head, we may or may not further work with the representation. Something we often kind of think about that working with as a rehearsal. These two stages, encoding and rehearsal, represent aspects of learning that can vary. These are the how of learning in the information processing approach. There are many ways we encode information, and there are different ways we rehearse it once we have it encoded. On some later occasion, we may have to retrieve that representation in order to demonstrate our new learning. And the basic approach to studying learning from this perspective is often verbal learning, that is, learning of lists of words. We ask people in verbal learning paradigms to learn lists of words, lists of word pairs, to demonstrate their learning in tests of memory for those words or word pairs. And although a lot of the research I'll talk about has been done with lists of words, you can use a similar approach with pictures or sounds or spoken languages, numbers, other kinds of stimuli. There are many options. But when we take this approach, we divide the learning process into 3 information processing stages. Let me first describe these stages, and then we'll need to briefly consider why this stage-like understanding is a little bit oversimplified. Encoding. During encoding, people are taking in new information and they're making sense of it. For example, as I'm talking, you're decoding the meaning of the words and the sentences, and you're understanding what I'm saying. As you do so, and this is important, you're not just focusing on what I'm saying. You're transforming it in light of what you already know, including the meanings of the words and how they're connected in the sentences I'm using. But you're also using what you know in terms of what you know about the concept of coding and what you understand stages to mean, and so on. You may not be specifically or deliberately aware of all the past knowledge you're using to do this encoding. The important point is that you're both hearing what I'm saying and you're drawing on your past experiences to transform the sounds I'm making into something meaningful and understandable. In fact, encoding operates through a variety of short-term information stores, and within each of those stores, information is being transformed. For example, if I present you with a list of words, it's represented as sensory information visually, if I'm showing you the words on a page, and then it moves to a short-term storage kind of space in the mind within which you can work with or rehearse those presented words. And that storage space is called, by researchers, working memory. Within working memory, we engage in processes that we refer to as rehearsing the words. We think about their meanings, we link them to memories we already have, and so on. And those processes of rehearsal also draw on our established knowledge, which you can think of as long-term memory. Encoding is central to our understandings of learning today. We're going to have a lot to say about how differences in encoding matter for how well we learn. The other 2 parts of an information processing approach apply, in a way, to issues of how well learning sticks once we've done it and how we can demonstrate learning. And these are called storage and retrieval. Storage in an information processing account refers to keeping information we have learned over time. And ultimately, the way things are stored depends on long-term or lasting changes in the way our neurons connect with one another. This is something referred to as long-term potentiation. The storage part of the process of learning is actually the most difficult to test, measure, or observe, and we won't say much about storage except for the last piece of information processing, which is retrieval. During retrieval, people make use of the information they previously learned. And this can take a variety of forms. For example, you might be asked to recall information. You might have to remember how to get to your new office or to recite the multiplication tables. You might need to recognize something previously learned. For example, can you recognize the face of the person waving at you? Or can you correctly recognize which coat is yours from all the coats in the closet? Or you might demonstrate use of prior learning without even thinking about it. Every time you shift gears in a manual transmission car, you're retrieving a previously learned motor skill, but you're not aware of that process at all. Your conscious experience is that you want to shift, and you do so. Now, retrieval is not the same as learning, and we might think of retrieval roughly as memory. It is important because retrieval is often one of the only ways we have of knowing that something has been learned. So retrieval is not the same as learning, but it's often going to be how we demonstrate that we or someone else has learned something. For example, you know your child has learned something in school when she can tell you about it, and in telling you, she has to retrieve the information she has acquired. Or recall the idea of shifting your car. Even though you're not conscious of the act of calling up or retrieving that motor skill, the fact that you shift requires you to retrieve a specific motor pattern. What I want to point out today is that retrieval is not only a demonstration of past learning, it's also a re-encoding. That is, every time you recall information, you re-encode it. You don't pull it up, then put it back just the way it was. You retrieve it, you use it, and the information is actually changed because you've retrieved it and used it. In this way, although retrieval often gets thought of as a way of demonstrating previous learning, it turns out retrieval is also an important way to improve learning over time. We'll talk more about this in a later lecture. Information processing approaches to learning, then, they often divide things into phases of learning and the demonstration that learning has been successful and, of course, retained. But you may be thinking, how is this better than the stimulus response and stimulus association approaches of conditioning research? Well, let's consider some of the issues that conditioning work did not address very well. Let's start with variation in rewards. Remember that conditioning couldn't explain why sometimes water is rewarding and other times it's not? Information processing says that encoding is a function both of the stimulus, the water, and the prior experience of the perceiver, and that experience varies over time. So, when an animal or a person's recent experiences have left them hungry, food rewards are enticing. When this is not the case, food rewards are less appealing. And in fact, in our broader who, what, when, where, and why framework, our experiences make each of us a very unique who. And as unique who's, what's going to reward us and reinforce behaviors for us is going to vary from one person or animal to the next. Because of this, one major factor in learning involves the way that our previous experience changes how we encode information. We'll focus more on this issue in the next set of lectures, and we'll return to it later in the course when we think about how different people do or do not learn differently. Now, a second issue that was poorly explained by conditioning was the idea of latent learning and observational imitation without any rewards. Conditioning paradigms have a hard time explaining why people would learn without rewards or incentives, although they do. Information processing theories, by contrast, suggest that we're fundamentally oriented towards making sense of our world. We want to turn what's going on around us into meaningful information. Information processing paradigms actually imply that information is its own kind of reward. So, like the alpine climbers who say they have to climb the mountain because it's there, we seem to learn stuff because it's there to be learned. Information processing accounts are particularly useful for thinking about what we learn and how we learn it. In conditioning work, variability in how people or animals learned was limited to variations in the way that stimuli were presented or that responses were rewarded or punished. And what happened inside the minds of those people and animals was off limits or unscientific. So there wasn't any way to ask, what sense did the rat make of the lever and the food reward? By contrast, in an information processing paradigm, we can actually look at variability in how people engage with the material to be learned. We can ask, in limited ways, what's in the rat's head, and in less limited ways, what's in the person's head. So when studying humans, we often do this with verbal materials, and the results can be really interesting. First, consider that some things don't help us to learn. For example, when I was young, and I needed to phone someone with an unfamiliar telephone number, I looked up their number in the phone book, and then I walked to the telephone on our wall, muttering the number over and over and over again under my breath until I could punch it into the touchpad. But after doing this, I didn't retain that phone number later on. It wasn't a good way to learn a telephone number. And in fact, numerous studies show that simply repeating information over and over doesn't actually help us to learn it very effectively. Well, one could say the problem with that is that I might never have intended to learn the number. Suppose I was merely telephoning a person that I never will need to telephone again, a store, and I wanted to inquire about an item's availability, not a call I would need to repeat. And perhaps it would work better if I had intended to learn that number. Unfortunately, it turns out that merely intending to learn a list of words also doesn't help us to learn them. In one classic study, Hyde and Jenkins asked participants to look at a list of 24 words, and they saw each word for 3 seconds. And as participants looked at each word, they were asked to do one of two things. They were either asked to determine whether the word contained the letters A or Q, or they were asked to rate how pleasant the word was. Now, notice that the second task requires people to think about the word meaning, and we'll come back to that later. Now, in this experiment, half of the participants were told they would later be tested on the words, and half were not told. And the assumption here is that if you were warned about the test, you would have the intention to learn the test words. Then, as is often the case in these studies, everyone was given a recall test. If you looked at the results, you would notice two things. First, the participants who were told about the recall test and those who were not told had exactly the same performance. The promise or the threat of a test didn't help anyone learn the words better, so presumably the intention to learn the words didn't really help. Second, the participants who thought about whether the words were pleasant or unpleasant recalled more words, just under 70% of the words, than did the people who determined whether the words were spelled using A or Q. Why would this be? While intentions to learn material and simple repetition don't seem to help us, something called elaborative or deep encoding does. And this is one of the most robust findings in the literature on learning and memory. Study after study reinforces this finding, and it has direct application to a lot of the learning we do. Here's what it means in real terms. Going over notes is less effective than reading and thinking about how material can be connected to other things we already know, or thinking about clever mnemonic devices that would help us recall material, or otherwise engaging in deeper, more elaborated thinking about the material we're trying to learn. There is a twist in all of this, however, which is that elaborative encoding works better for learning because, in most cases, it approximates how we're going to use the information we're trying to learn. In the laboratory, you can actually create circumstances where this is not the case. For example, imagine that I give you a task where sometimes you have to come up with a rhyming word. Thinking about a rhyming word is usually a type of shallow processing or shallow encoding. Now, on a different task, you might have to think about whether a word fits a sentence in terms of meaning. This is usually viewed as a deep or elaborative processing task. Then I might give you two different kinds of retention tests to see what you've learned. In one test, you have to look at words and tell whether you've heard those words before or not. The usual advantage for elaborative or deep encoding is observed here. People who thought about whether a word's meaning fit the sentence did better, and people who identified rhyming words did poorly. Now, in the other test, you're given a list of cue words that rhyme with the original list of words, and you have to use the cue words to recall the list words. In this case, the rhyming participants actually outperform the deeper processing people. What's going on? This is a phenomenon called transfer-appropriate encoding. And what it means is that the more your learning method, the more your how approximates the way you're going to need to use the information you're learning, the better your learning will be. In fact, if you're learning specifically to be able to do well in a test, testing yourself over and over again represents a way to learn material that's very effective. Studying the booklet for the driving test can help you pass the driving test, but studying for that test won't necessarily improve your driving. Now, I mentioned earlier that every time we recall things we've learned, that occasion of recall functions like a new learning episode. Another way of saying this is to consider that when you engage in retrieving learning, you give yourself another shot at encoding. And there is a phenomenon called hypermnesia that shows just how effective repeated retrieving can be for learning. Now, what is hypermnesia? In order to explain this concept, I'm going to have to tell you about another experiment. Erdely and Kleinbart showed participants 60 slides. Now, some participants in their study saw slides of simple picture sketches of objects, like a telephone. Other participants saw instead the word telephone on the slide. Participants looked at each slide for about 5 seconds, and at the end of the presentation, participants were given 7 minutes to remember as many of the items they had been asked to learn as possible. On subsequent days, participants in this study were asked to complete recall sheets at least 3 times a day over the course of the next week, and each time they were to take only 7 minutes to recall. If you plotted their results on a graph with the y-axis indicating the number of items people remembered and the x-axis showing the time since they initially learned, you would see distinct patterns for the two kinds of items over time. For the first several hours, you see a sharp rise in the number of items recalled for both pictures and words. Then the number of words recalled stays stable at about 50% recall, and the number of pictures actually increases to about 66%. So there are 2 things I want to draw your attention to here. First, both words and pictures show increases in retention over repeated testing. What is this about, and how does it relate to learning? This is the phenomenon of hypermnesia. What it means is that when you test retention, when you engage in testing over and over again, you actually end up increasing what you remember over time. And this is a very powerful and important idea for those of us who want to continue to learn things or to remember what we've already learned. Testing or trying to recall things increases your chances of learning and retaining what you've learned. Now, the second thing I want you to think about with respect to these results is that the data actually suggest different types of information may be differentially easy or difficult to learn. And the study actually suggests that pictures may be easier to learn than words. And this is why so many memory techniques, a topic for a different course, make use of visual imagery to help people remember things. But let me get back to learning and forgetting. Material we learn is forgotten when it's not used, and retention testing is also a way of using the material we've learned. Now, in some cases, as with reading for many of us, we retention test ourselves on reading every single day. But in other areas, for example, with foreign language learning or solving math problems, we may actually not very frequently make use of that past learning. And it's not surprising that we then end up forgetting or losing much of what we initially learned. So it happens that there's actually a substantial body of research looking at the forgetting of material that was learned over time. And some of this work is actually quite old. For example, Ebbinghaus, around the turn of the century, asked people to learn lists of nonsense syllables and showed that after people learned the syllables perfectly, that is, they could recall 100% of what he had taught them, their performance on a retention test tended to decay over time. That is, over time, when they didn't use these nonsense syllables, they lost them. They no longer had access to that learning, or they unlearned. So, classical conditioning helped us look at associations, but it didn't let us think about consequences. Operant conditioning let us think about rewards and consequences, but not why some things were rewarding and some things weren't, or things were sometimes rewarding and sometimes not, or why people actually learn without rewards. And both of these approaches assumed that what the person or the animal knew or previously learned didn't quite matter for how they were going to learn something new. What we've talked about today is how essential it is to think about learning in terms of information, representations, expectations, and rules, and to understand that learning happens as a process of encoding, retrieval, and re-encoding. What kind of information matters? Pictures are easier information than words. Why we are learning matters. If we learn in ways that don't actually correspond to what we need to do with our learning, it's actually going to be less effective for us. How we deal with information also matters. Thinking about material, connecting it to what we already know, elaborative or deep encoding usually works best for learning. And elaborative encoding brings me to what is perhaps the most important part of the information processing approach. Information processing approaches demand that we consider not just the material that's going to be learned, but also the past experiences and the expectations that we bring to that learning experience. In other words, there is, as we'll discuss in more detail next time, no tabula rasa. There's no blank slate in learning. Instead, we bring to every learning experience our intentions and expectations based on our broader goals, our perspective on what we are learning, and our shared and unique cultural history.